video, I'm going to talk about these objectives here. And again, a lot of the stuff that you're going to see in this lesson is just a continuation or like the same kind of thing with just a little bit of a twist to what we've been doing with integrals. We're going to do kind of a basic integration problem using our understanding of antiderivatives and the fundamental theorem of calculus. We'll talk a little bit about the net change theorem and your experience with the net change area and the total area, that kind of stuff, to help us solve some application problems. And then at the end, I'll talk a little bit about the interesting thing about the integrals of odd and even functions. Okay, so let's start with this question here, where I'm going to essentially use my understanding of calculus from the first semester to help me integrate this definite integral of 1 to 4 of the square root of t times 1 plus t times dt. Again, dt is that dummy variable. Okay, so first thing I'm going to do is I'm going to rewrite t, the square root of t, as t, we'll change colors here, t to the 1/2 power. Okay, so this is going to be t to the 1/2 power times 1 plus t. And you'll notice I'm not using any integral right now. I'll bring it back once I get to a place where I'm ready to actually do the antiderivative. So t to the 1/2 power times t is t to the 1/2 power plus, and t to the 1/2 power times t is going to be t to the 3/2 power. All right, so now I'm trying to find the integral between 1 and 4 of this function times dt. All right, so I'm going to find the antiderivative, and I know that the antiderivative for t to the 1/2 power is going to be t to the 3/2 power, right? Because when you subtract 1 from that, you get 1/2. And I need to put 2/3 in front. Plus, this is going to be t to the 5/2 power, and I needed to put 2/5 in front. Again, I could write plus c, but ultimately I'm going to choose c is 0. So this is my antiderivative. So if I evaluate this at 4 and then evaluate it at 1 and subtract it, I will find the value for this integral. So I'm going to do my math here. I mean, 2/3 times 4 to the 3/2 power plus 2/5 times 4 to the 5/2 power, right? All of that subtracted. Now I'm going to do the same thing for my 1. So 2/3 times 1 to the 3/2 power plus 2/5 times 1 to the 5/2 power. Okay, so whatever I get there is going to be the value for my definite integral. So I'm going to move to Desmos so I can type this all in. All right, so I have Desmos here. I have 2/3 times 4 to the 3/2 power plus 2/5 times 4 to the 5/2 power, right? So all of that, and then minus, same thing here, 2/3 times 1 to the 3/2 power plus 2/5 times 1 to the 5/2 power. All right, so you can write it as a decimal if you want, or as a fraction. 256 over 15 is the fraction. 17.06 repeating is our decimal. All right, so that's going to be it for our first one. That is the area under the curve of this function between 1 and 4. Okay, let's try talking about the net change theorem. So essentially what this is saying is that if there's a new value of a changing quantity, you take your initial value and you add it to the integral of the rate of change. So you'll notice this f prime of x, that's the derivative of the antiderivative, which is kind of like your starting value or your starting function. And the key thing here is if they shuffle it around, you'll notice that that looks extremely familiar. We've been working with that for a couple lessons now. That's part 2 of the fundamental theorem of calculus. So ultimately, this is going to help us find the new value of the changing quantity. Okay, so let's use that to find the displacement of this particle, looking at a velocity function between time 0 and time t equals 3. okay? So ultimately, what I'm going to do first is I'm going to find the integral between 0 and 3 of this function, this velocity function, which is going to be 3t minus 5 times dt. And you guys remember in our talks in the first semester about how if you start with the displacement or position function and move to velocity, then move to acceleration, it's all variations on derivatives. So this idea is if I take the integral of the velocity function, right, the integral of this velocity function would actually give me the position, which would help us find the displacement. So essentially, this is an application of your understanding of stuff from the first semester and the stuff from this semester. All right. You know what? Before I do this with the calculus and the algebra, let me just kind of visually show you what I'm talking about here. So if I plot 3t minus 5, and I'm looking at between 0 and 3, you can see right here that I'm looking at my two triangles, right? There's one here and there's one here. And so ultimately, when I'm trying to find the net displacement, I'm going to be finding that area underneath that curve. In this case, it is a line again, okay? So let's find the antiderivative of 3t minus 5. So if I write t cubed and take the derivative of that, I'm sorry, not t cubed, my bad, t squared, the derivative of t squared is 2t, but I don't want 2t, I want 3t. So I need to put the fraction in front, 3 halves, because 3 halves times 2 is 3, okay? Then the antiderivative of 5 is going to be 5t. I could write plus c, but I'm going to choose c as 0, so this is my antiderivative that I'm choosing. So I'm going to evaluate this right here at 0 and 3, and then subtract them. So I have f of 3 minus f of 0. So that's going to be 3 halves times 3 squared minus 5 times 3 minus 3 halves times 0 squared minus 5 times 0. So whatever that is in decimals is going to be my area under the curve here, which essentially is our net displacement of this particle. All right. Now, you can plug in all of this. You'll get the right answer. But I know that 0 squared is 0. 0 times 3 halves is 0. 5 times 0 is 0. All that 0. So really, I just care about plugging in 3 to this function. So I have 3 halves times 3 to the second power minus 5 times 3. All right. So again, minus 5. That ain't it. 5 times 3. There we go. So your answer, if you want to put it as a fraction, is negative 3 halves. As a decimal, it's negative 1.5. So this is going to be negative 1.5 meters is the net displacement here for this particle. So negative 1.5 meters. Okay? Now, let's talk about how we're going to find this next one. It's a little bit more challenging, talking about the total distance. So I'm going to kind of take you back to a few lessons ago when we talked about the total area. All right, so that's where when you have some triangles that are, or a triangle that's in the positive y values, triangle that's in the negative y values, I don't actually care about that. All I care about is finding the areas and adding them together. So if you look at this graph, right, you'll notice that we actually, all our y values are negative until this point here, 1.6 repeating comma 0. So I'm going to chop this up, all right? I'm going to first show you it all together. But essentially what I'm going to do is I'm going to chop up these two intervals separately. All right, so my integral, my first one's going to be 0 to this value of 1.6 repeating, which you'll see is going to be that 5/3. And then the second integral is going to be from 5/3 to 3. So I'm essentially going to do two things here. All right, so let me first just write my integral is going to be from 0 to 3 of my velocity function, 3t minus 5, times dt. But again, I'm not doing the same thing as I did before because it wants the total distance. So this is where I actually don't care about the negative values or the positive values. They're all going to be absolute valued. So let's show you real quick how I got that 1.6 repeating. If you set this equal to 0, you'll have 3t equals 5 and t equals 5/3, which is 1.6 repeating. So essentially, I'm going to be doing the integral from 0 to 5/3, all right? And this is going to be the negative version of this, all right? So the opposite of our 3t minus 5 plus the integral from 5/3 to 3, and those are the positive y values, so 3t minus 5. Okay, so doing this work, right, these two definite integrals, if I find those areas under that curve / line, that's going to give me my total distance traveled. All right, so let's find the integral here. All right, so first thing I'm going to do is I'm going to put that negative, distribute it, and get negative 3t plus 5. So that antiderivative is going to give me, it's going to be t squared. Again, I don't want, when I distribute that or take the derivative of t squared, I get 2t, but I want negative 3. So I'm going to put negative 3/2 in front plus 5t. So that's my first antiderivative. And my other antiderivative, right, from this one up here is going to be the same one I used before, right? That antiderivative of 3t minus 5 was 3/2 t squared minus 5t. So 3/2 t squared minus 5t. Okay, so I have two slides here. So I'm going to take essentially that first one, that first antiderivative, plug in 5/3 and 0, subtract that, and get my value for the first integral. So I'm going to do f of 5/3 minus f of 0, and I'll put the first antiderivative one up here, which was negative 3/2 t squared plus 5t. So I'm doing that for that one. Then this one, which was 3/2 t squared minus 5t, that one I'm doing f of 3 minus f of 5/3. All right, so now let's do all the work here. So I have negative 3/2 times 5/3 squared plus 5 times 5/3. I'm not going to plug in the 0. You can plug in the 0 if you want, but I know that if I plug in 0, I just get 0. So that's going to give me whatever that is my value for the first integral. The second one, I need to do all the work again. I'll show it, but you'll notice I've done some of it already. So plus, right, this is going to be plus of 3/2 times 3 squared minus 5 times 3. That's the part I already did. Minus 3/2 times 5/3 squared minus 5 times 5/3. Okay, I know that's a lot going on, so let's kind of chop it up for you in Desmos so you can see all the pieces that I'm finding. So I'll first plug in the 5/3 into that first antiderivative of negative 3/2 times t squared plus 5t. Okay, so let's do negative 3/2 times 5/3 squared plus 5 times 5/3. Make sure I got the right stuff. Negative 3/2 times 5/3 squared plus 5 times 5/3. Great. You can put that as a fraction if you want, or a decimal, your choice. I got 4.16 repeating. So I'll write that down, 4.16 repeating. Okay. And then plus, this is going to be a little bit more work here. All right, so that's 3/2 times t squared minus 5t, plugging in 3 first. So a new line here. So 3/2 times 3 squared minus 5 times 3, whatever that is, minus, same thing, but I'm plugging in now 5/3 squared minus 5 times 5/3. All right, and I get 2.6 repeating. So now if I add these two together, right, 4.16 repeating, or 4.16 repeating plus 2.6 repeating, right, you can see that I get approximately 6.83 repeating. All right, if you wanted to, I think we can actually get the fraction if you want. So 25/6 plus 8/3. All right? And so if you wanted the decimal, it's 41/6. So 6.83 repeating is going to be my answer. I'll write this one down again. So that was 2.6 repeating. So my total distance traveled by the particle, because again, I don't care about the fact that we've got some of it is negative, some of it's positive, is going to be 6.83 repeating. Or if you wanted the fraction, 41/6. All right, so that's, hopefully you see how that's a little bit of a continuation from something we did a few lessons ago. Okay, now let's do one more application, then we'll get into looking at even and odd functions and the interesting things about those. So we have a motor on a motorboat is started at t equals 0, and the boat consumes gasoline at this rate. We have 5 minus t cubed gallon per hour for the first hour. How much gasoline is used in the first hour? So I'm going to integrate this from 0 to 1, right? 0 hours to 1 hour of my 5 minus t cubed dt. All right. And so we're just going to use our understanding of antiderivatives. That's going to be 5t, right? The derivative of 5t is 5. Watch how I do this one. I start with t to the fourth power, but when I take the derivative of t to the fourth power, I get 4t cubed, but I don't want 4 in front of there. So I got to put that fraction of 1/4 to make sure that it becomes a 1. So this is my antiderivative. You could write plus c, but you know, as I've said many times already, I'm choosing c is 0. So I'm going to evaluate this at 1 and 0, and that will give me the gasoline used in the first hour. So 5 times 1 minus 1/4 times 1 to the fourth power, whatever that is, minus 5 times 0 minus 1/4 times 0 to the fourth power. Again, right, when you look at this one on the right side, 0 times 5 is 0. All that's going to be 0. So I'm really just caring about plugging in the 1. So I'll go to Desmos. I don't know if you really need Desmos for this. You can probably see what the answer is pretty quickly, but I'll show you in Desmos in case you're having some trouble. All right, so I'm going to type in 5 times 1 minus 1/4 times 1 to the fourth power. So 4.75 is going to be our answer. We'll get you the units there. So we have 4.75 gallons of gasoline have been used in the first hour for this boat. Okay, so the last thing. All right, the last thing is something interesting about integrating even and odd functions. And I'm going to start with even functions. And the most basic even function that we've ever talked about in any math class in high school, right, for an even function is y equals x squared, right? And even functions have, if you remember this, y-axis symmetry. All right, so let me just show you when we plot just x squared, and then show you what this rule is actually stating. All right, so here is y equals x squared. All right, let me zoom it in for you. Boom. Okay, now if you look at the rule, it says that if you're looking at the integral from the opposite of a number to that number of this function, and you know the function is even, then essentially you can just do the integral of 0 to that number of your function and double it. All right, and let me show you why. I just chose, since we already kind of have it here, I just chose the limits of my integration to be -2 to +2. So hopefully if I type that in, you can see that these are exactly the same amounts from my area under the curve on this left side from -2 to 0, and on this right side from 0 to +2. Okay, so that's why you can just find one of these. Usually you find 0 to the positive number. So find that, and then you double it. So that's what's interesting about integrating an even function. All right, so let me do that one first, and I'll come back to the odd function. So let's integrate this even function. We're going to do it twice. On this slide, I'm going to do it just straight up. And on the right side, I'm going to use that rule that says you can just find the integral from 0 to the positive number and then double it. All right, so here we go. Let's find the antiderivative of 3x to the 8th power minus 2. So I know it needs to be x to the 9th power. When I take the derivative of x to the 9th power, I get 9x to the 8th power, but I don't want 9, I want 3. So I'm going to put 1/3 in front because 1/3 times 9 is 3. Minus 2x. All right, this is my antiderivative. Let's go ahead and evaluate this at 2 and negative 2. All right, so I have 1/3 times 2 to the 9th power minus 2 times 2, whatever that is, minus 1/3 times negative 2 to the 9th power minus 2 times negative 2. Okay, so finding this will give me my area under the curve between negative 2 and positive 2 for this even function. All right, so let's type it in. Okay, so we have 1/3 times 2 to the 9th power minus 2 times 2, okay, minus 1/3 times negative 2 to the 9th power minus 2 times negative 2. Okay, you could write this as a fraction if you wanted to, 1,000 over 3, or you can write this as a decimal, 333.3 repeating. So 333.3 repeating. Now what I'm going to do is I'm going to do it again, but I'm going to use this rule that says I only have to find the integral, the limits of integration between 0 and positive 2, and then I'm going to double it. So essentially what I'm going to rewrite is the integral from 0 to 2 of 3x to the 8th power minus 2 dx, and then I'm going to, at the end, I'm going to double it. Okay? So I'm going to use the same antiderivative as before, which was 1/3 x to the 9th power minus 2x, but now I'm evaluating at 2, at 0, so I'm going to do 1/3 times 2 to the 9th power minus 2 times 2. Again, you can do this again and do 1/3 times 0 to the 9th power minus 2 times 0. But as I've been saying before, right, a lot of times with the 0, it's just going to be nothing. So I just care about plugging in the 2. All right, so 1/3 times 2 to the 9th power minus 2 times 2, which I think I have some of that right here. So there it is, 1/3 times 2 to the 9th power minus 2 times 2. So that is 500 times, or 500 thirds, or 166.6 repeating if you double it. So 2 times 500 thirds, you get the same answer we had before, which was 1,000 thirds. All right, so just verifying that when you do 166.6 repeating, but then you multiply that by 2, you get the same answer. All right. Again, you wouldn't have to do this twice, but I'm just showing you how that rule is true. Let's do the same thing with this last odd function. Actually, before I do that, let me go back to the odd function rule and show you what's interesting about that. So the most basic odd function we've ever talked about in any algebra class is y equals x cubed. And if you remember about odd functions, they have what is called origin symmetry. So let me plot y equals x cubed for you so you can see why this rule is what it is. Okay, so we have x cubed, right? And I'm just going to do the same thing I did before, so you can kind of zoom in and see it. All right, so if you look between negative 2 and positive 2, right, between negative 2 and 0, these are all negative y values. And between 0 and positive 2, these are all positive y values. So if you were to find the integral between negative 2 and 2, right, those are just going to cancel each other out and become 0. So that's why this rule states that if you have a continuous odd function, the integral between the opposite of number to that number of an odd function is going to be nothing. Right, it's going to be 0. So we're going to do the same thing. All right, I'm going to use my understanding of integrals here to kind of show you why the integral of this odd function is going to be 0. Right? Before I even do it, I know it's going to be 0. So we do the integral of from negative pi to pi of negative 5 sine of x dx. Now, the first thing I noticed is there's a -5 in front of that sign. So what I'm going to do is use one of my properties of my integrals from last lesson or a couple lessons ago and actually just move that to the front. Right, so the -5 is going to move to the front in front of the integral. And now I'm doing the integral of -pi to pi of sine x dx. Okay? So now, when I look at this, right, I am going to be trying to find the antiderivative for sine of x. Well, I know that the derivative of cosine of x is negative sine x, but I don't want a negative sine x. I want a positive sine x. So I'm going to throw that negative sine x in front of there, okay? Now, I do have that -5 that's going to be happening there. And so when I do this, I'm going to kind of ignore that -5 until the very end. So I'm going to find the integral of I'm going to use my antiderivative of negative cosine of x evaluated from -pi to pi here. So I'm going to do that by plugging in and doing f of pi minus f of -pi. So that means I have the opposite of the cosine of pi minus the opposite of the cosine of -pi. Again, that's not going to be my answer because I am going to take this and multiply it by -5 at the end. All right, so I'm going to move to my next slide. And you can use Desmos if you need to. I know from my days of trig that if I do my quadrantals, pi is over here, right, and -pi if you move the other direction. So that ordered pair is going to be -1, 0. So the cosine of pi or -pi is going to be -1. So this becomes -5 times, it's going to be the opposite of -1, which is 1, minus the opposite of -1, which is 1. You should notice 1 minus 1 is 0. So -5 times 0 is 0. So just confirming that the integral of this odd function is 0, which we knew going in. Now let me show you in Desmos the graph of -5 sine of x over that integral of -pi to pi, so you can confirm visually as well. All right, so we have -5 sine of x. And I'm looking at between -pi and pi. Right, so here's pi, and when you look at it, right, if you look at the area over here between -pi and 0, those are all positive y values. Then you look at 0 to positive pi, those are all negative. And so when you find the area under these curves between the x-axis and that curve on those intervals, those are going to be opposites. When you add the opposites, you end up with 0 right here. Okay, so that's it. Hopefully you guys can try some of these homework problems and solidify these concepts. Good luck.